Okay, welcome back. Yeah, this is lecture 12. The idea for today is first we'll end our discussion, or at least the first version of our discussion on first countable spaces. And then we'll start with the quotient topology. So remember what we were doing last time. These are the notes from last time. We introduced the notion of first countable spaces. And those are spaces where for each point you have a basis of neighborhoods, which happens to be countable. That means at most as infinite as the positive integers. And the fundamental thing about that is if you are in a first countable space, you can think, this is of course not true, but you can think that you have bases that behave like these ones on metric spaces. So for metric spaces, we have this very convenient basis at each point, which is take the all bolts center at X and let the radius decrease as 1 over N. And that's kind of the thing that's going on any first countable space. So we proved, this was our Fremius lemma 3 from lecture 11, that whenever you are in that situation, so if you're first countable, then for each point, you can always construct a basis of neighborhoods that decreases. And then for any such basis, and any sequence with the property that the nth value lives in the nth basis set, then that sequence will converge to your point X. These two were the main ideas from last time. And the upshot here should be, if we have this condition using this basis, we should be able to somehow describe the topology using sequences. So this is the last part of the last lecture. We introduced these two definitions. Suppose you have two topological spaces. So notice here, things are not first countable. We're going to define something that's independent of that. We said that a subset of X is not closed, but sequentially closed if whenever you have a sequence inside that subset, which you know converges to something, then something needs to live on your subset A. And then we defined a sequentially continuous function, that's a local notion. So at each point, if whenever you have a sequence converging to that point, and you apply f to the sequence, you can be sure that the sequence that you got is going to converge to f of x. So starting from there, for today's class, the first theorem will be let's take two topological spaces. I want to at least justify the words I'm choosing. So the first statement is, so the following will hold, 1 and 2. The first statement is just about X. If we have a subset of X, which is closed, then it's sequentially closed. And the second one is, if you have a continuous map from X to Y, that's why I took topological spaces, is continuous just at the point X, then it's sequentially continuous. At that point. So the proof of this, I will not go through the proof. This will be homework. But I want to at least give you an idea for one. So the idea is something like you have a closed set. You want to show it sequentially closed. So how do you start such proofs? You start with a sequence, xn, be a sequence in A, in your set that you're assuming is closed, And you need to assume it converges to something. Maybe let's just write with xn converges to some x in x. And what we want to show, definition of sequentially closed, we want to show that the limit point is actually an element in A. So how do we show this is the case? The idea here will be, well, assume it is not. So the idea is the complement of A is open. So if X is not in A, which means X is in the complement, then X minus A is a neighborhood of X. And now Xn converges to X, and we're in trouble. Because if it converges to X, eventually it needs to live in X minus A, which will contradict the fact that the sequence lives in A. So that's the idea. Of course, you need to continue from here. And for 2, well, you need to start somewhat similar. But let's just say this for the moment. So this will be a homework assignment for yourself. Now, the important thing now, remember, we're supposed to be studying first countable sets. So the second theorem for today, it's going to be about first countable sets. And it's going to say, in the same situation as before, so same situation as before, set up as in theorem 1. If our set X is first countable, then the converses of 1 and 2 will hold. So this means a set is closed in X if and only if it is sequentially closed, and the function going out of X is continuous if and only if it is sequentially continuous. So let's prove the converse of 1. So what we need to do here is assume we have a sequentially closed subset of X. Sequentially closed. And what we want to show is that A is closed. And equivalently, that's just equivalent proving that the complement X minus A is open. And how do we prove that a set is open? Well, we prove that a set is open by proving that it's a neighborhood of each of its points. So let X in X minus A, we show that X minus A is a neighborhood of X. How do we prove this? Well, we need to use first countability. So like we can use our famous lemma from last time. So this was lemma 3 from lecture 11. We know there is basis, neighborhood basis. Let's call this B sub X, which is countable with the property that it decreases. So Vn plus 1 is a subset of Vn. Okay, of course, here we're using that our space X is first countable. And we want to show, remember, this is what we're trying to prove, X minus A is a neighborhood of X. So To prove that, we'll claim that some Bn for some n, Bn needs to be a subset of x minus a. Notice that if we prove this, then x minus a will be a neighborhood of x, because Bn is a neighborhood of x, and we'll be done. So how do we prove this? Well, usually we go by contradiction. So assume that's not the case. So if we assume that for a contradiction that that's never true, what we actually have is that Bn, if it is not a subset of x minus a, it means that Bn always intersects a, non-trivial. So this, maybe I can be more clear. So assume for a contradiction that Bn is not a subset of the complements, and this for any n. Then, as a consequence, or equivalently, Bn, if it is not a subset of the complement, intersects a, non-trivial. And that's for any positive integer n. And now, as we discussed last time, using our axiom of choice, but just by intuition, we can, for each n, take some element in that intersection, which will depend on n. So let's call it xn. We can do this for each n. So let me move this for each n. We'll take some xn in the intersection, which we're assuming it's not empty. And now we can consider the sequence that they form. This sequence is going to have two very useful properties for us. And I really need a sequence because the only assumption that we have is that A is sequentially closed. That's stating something about sequences. So you shouldn't be surprised that I'm trying to look up a sequence. Now, this sequence has two properties. The first one is xn lives in Bn for every n. So by our lemma 3 from last time, that means, or that's enough to show that xn will converge to x. But now, xn is not only here, this is what I'm using, but it's also here on A, in A. So since xn lives in A for every n, and it converges to this x that we don't know if it's an element of A or not, by definition of this sequentially closeness, what we can be sure of is that x needs to be an element in A. The limit point of the sequence in A needs to live in A. Okay, x lives in A, that's not okay. Because, let me go up, we started with an element in the complements. So that's the contradiction that we were trying to get. This contradicts that x is in the complement. So this means our claim needs to be true. The claim is true, which means that for some positive integer, the neighborhood Bn needs to live inside x minus a, which means that x minus a is a neighborhood. Of our point x. And this is for any x in the complement, which means x minus a is open, which means x is closed. So that's the end of part 1. Okay, that was an instructive proof, mostly trying to cook up a sequence. That was the most difficult part here. But then, of course, we need to work even more. So the second point is now we need to assume we have a sequentially continuous function at a point and need to prove it is actually continuous. So the idea would be very similar, but I want to go through it. So statement 2, here we assume that our function f, which is a function going out of x to y, is sequentially continuous at some point in x, in the domain, at small x in the domain. So what we want to show is that f is actually continuous at x. So we want to show that for maybe instead of writing this, I will say take a neighborhood of f of x in y. And what we want to show is that for some neighborhood, u of x in the set x such that u is a subset of f inverse of p, the preimage. So as before, let's take a countable basis at our point, which decreases. I'm using the same lemma. Notice that whenever I use that x, the space x is first countable, I'm just using always this particular basis. So for this basis, we'll claim that the u that we're trying to find, so remember I'm trying to find some neighborhood u of x. What I'm claiming is one of these bn's will work. So the claim is there exists n such that bn is a subset of the preimage of the neighborhood v of f of x we took. And the proof is going to be very similar to the previous one. So assume for a contradiction that's not true. So assume bn is not a subset of the preimage. So assume b of bn is not a subset of the preimage, and that's for every n. Now, if that's the case, then let's write what's happening. Then for each n, if bn is not a subset of the preimage of v, for each n, we can be sure there exists some point, let's call it cn, which lives in bn, but not in the preimage of v. And now again, we form a sequence. So maybe instead of saying exist, let's say take. We know it exists because the set is not empty. That's what we're assuming for a contradiction. And I can take a point, and now we can consider the sequence they form. Okay, so what about this sequence? Again, this sequence will have two very important properties. The first one is that it's always an element at the nth entry, we have an element in the nth basic set. And this is for any n. So using our lemma, we know that Cn will converge to x. But we also know that our function is sequentially continuous. That's the only thing we're assuming. So we get that when you apply f to the sequence Cn, it needs to converge to f of x. That's the definition of sequentially continuous, or sequential continuity at the point x, I should say, at x. Okay, so we have this, Cn converges to x, and as a consequence, this. And remember, I have this v, which is a neighborhood of f of x. That's how everything started. So as a consequence of this, maybe I can say, since v is a neighborhood of the limit point f of x, we know that for some integer, and actually for every other integer bigger than this one, our sequence f of Cn will live in V, because V is a neighborhood of the limit point. And now this is a contradiction because of this. So we know this, but this contradicts. So this contradicts that Cn is not in F inverse of. So in other words, our claim is true. There exists some positive integer such that Vn is inside the preimage of V, and that's all we need to do. F inverse of V, preimage, is a neighborhood. Yeah, that's all I need to show. That's all I need to show. And that's the conclusion of this theorem. Okay, so the upshot here is what we are saying. Maybe I can write that very quickly. So if x is first countable, then what we're saying is, one, we can describe closed sets in X using sequences. That's the first part. I should say using sequences that converge. And if we can describe closed sets, then we can describe the topology, because the open sets are just their complements. And two, can describe continuous functions going out of X. Again, going out of X using sequences. So using the same. And that's something to keep in mind. So sequences are very powerful if you live in a first countable space. Okay, so this is all I want to say about first countable spaces, but we still have like more than half an hour. I'll recommend you pause the video now, and we'll start with and take a break for a couple of minutes, and I will start with a quotient topology. So here's what I want to describe about quotient spaces. What I'm going to say now in this class is, at some point we want to get into chapter 22 in markers. But what I'm going to say now is mostly introductory. So not really about topology. It's mostly about equivalence relations, and because that's what's behind quotients. So a refresher on equivalence relations. We also discussed this on the first lecture, but I'm going to be more to go into more depth. So relation, I should say probably a binary relation on a set X is a subset of the Cartesian product of X with itself. And usually you denote that by R. And the very usual notation is we denote x related to y with this tilde instead of the pair x comma y lives in R. So it's easier to use this sort of notation here. And now we don't really care about any relation. We want our relations to be something else or something more. So this relation R is called an equivalence relation. So this is the new part, equivalence. If it satisfies three things, the first one is it needs to be reflexive. So that means x related to x for every x in the set. This is what we call reflexivity. The second fact is if you have x related to y, then y needs to be related to x. And this is for any x and y. This is what's called symmetry, the relation. And last property is what's called transitivity. If x is related to y and y is related to c, then x needs to be related to c. So you can like pivot on y to go from x to c. This is for any 3 points in our space, and this is what's called transitivity. So this is not new. We discussed this before. And what's important about equivalence relations? The following. So let's go through some constructions. So things that you not only can, but do whenever you have not only you can, but should do whenever you have an equivalence relation. So assume we have an equivalence relation on a set X. The first thing we can do is, so let's number our things. The first construction you can do is take a point, an element in X. You can define the equivalence class. So the equivalence class of the point or the element is going to be a subset of X that usually denoted by X between square brackets. And it's a subset of X which contains all points in your set which are related to the X you took. So what we're doing here is we're putting on a subset, all other things that are related to X. And now the idea is, well, you can do that for each point in your set X. So this word might be new. The quotient set of X under this equivalence relation is, well, this is the notation we used. X quotient by the relation. And here, what we're going to put is we're going to put all equivalence classes. So the equivalence class of X, where X is any element in my set X. So notice this is a collection of subsets of X. It's not really important that it's a collection of subsets, but it's sometimes useful to remember that if you're getting lost. So this is a new word. I'm quite sure this is the first time you've seen quotients for sets and their equivalence relation. But what we're doing is not new. We're just considering all possible equivalence classes. Notice, though, that this notation will usually repeat some elements in the set. So if X is related to Y, then the class of X will be the class of Y. In other words, this is not giving you a different element for each X. Things will be repeated. Now, I've defined the equivalence class of a point. I will define the quotient set. And now the last ingredient that you should always consider is the quotient map. So the quotient map is this following function. I will always use pi for this function, which goes out of your set X to the set of equivalence classes, the quotient sets. And it's given by, well, I really know what to do here. If you give me an element in X and I want to associate to it a class, well, I might as well associate the class of X. And that's for each element in the sets. So notice, by definition of the quotient set, this function is surjective, because everything here looks like the class of something. That's just by definition. So these are the three fundamental things that you can and should do whenever you have an equivalence relation. You can compute equivalence classes. You can consider the set of all equivalence classes, and that set is related to X in quite a natural way using this natural map here. Okay, so this is probably a new perspective on something you know. And if you're starting to get lost, I want to say some words in practice. Why do we care about equivalence relations? We use the quotient set to identify certain points in X, namely those that are related. Or maybe instead of saying the quotient set, I can just say we use equivalence relations to identify or to paste different points. And we will see examples of what I mean by this. We'll see one example today, another one next time. But the idea is, if 2 points are related on the set X, then they become the same on the quotients. So what you are doing is you are collapsing an equivalence relation to a point. That's what we're doing with the quotient. So let's illustrate what we're saying here. Example. So I'm going to give us to go back to something that we saw before. I'm going to take the closed interval 0, 1. For us, this is just a set at the moment, a subset of the real numbers. And here I'm going to define an equivalence relation. On this set. So let me first give you the formal definition, and then I will say what I'm doing. X is related to Y. So I take 2 points. If and only if either they are the same, or they both live in the extreme points of the closed interval, 0, 1. So what I'm actually doing here, in other words, under this relation, internal points, so internal points will never satisfy this, so they are only related to themselves. I'm not doing much on the interior here. But I'm identifying the 2 extremes, but 2 extreme points get identified. So what's going to be the equivalence classes here? So maybe let's say the collection of classes of this relation are going to be the following. So remember, we denote the set of all classes by this symbol here. Ax is 0, 1. What we're going to have here is for each x in the interior, we're just going to have the singleton x because it's not related to any other point. But now I have another class, and that class is just containing the two extreme points, 0 and 1. And I need this second bracket here because this is the element on the class, and then I'm taking the set for that element. Okay. What's going on here? Let's go with picture. So suppose this is the closed interval 0, 1. 0, 1. Whatever you want it to be 0 and whatever you want it to be 1, that's okay. Our relation here, what it's doing is, if you're any of these points, then you will not get identified with anything else. But these 2 points need to be somehow pasted in the quotients. A very instructive way to look at that is, well, I want to paste these 2 points. They should be the same. So you can take the line and just collapse the 2 extremes. And hopefully you are convinced what you're going to get is somehow a circle. So it's maybe starting from this point, you will get a circle like this. That's not a circle. Let's go again. Circle. Yeah, let's pretend I can do a circle. Okay. So what I'm doing is, for example, this point over here, it's going to live somewhere over here. And now these 2 guys will get identified. For example, this guy should go somewhere over here. Taking the 2 extremes, pasting it to something. Seems like we have a circle. So let me write that. Seems like our quotient behaves or looks like a circle. So let's say equals S1. But that's of course not true. S1 is a subset of R2, and here we're just having some sets in the powered set of 0, 1. So different nature. This is of course not true. This cannot be the same. So these 2 sets cannot be the same. Not the same. They look like, but they cannot be, and mostly because of the nature of these guys. So what's actually going to happen, we'll see this next time, is, or maybe by the end of today, there will be a bijective function between these 2 guys. So they are not the same. We can identify them with a bijective function. And that's making it very clear that we should be able to say how to define functions out of quotients. So I want to state a theorem about that. Here's our theorem. Very important theorem about quotients. So functions, by quotients, I mean quotient set. So the quotient of a set by an equivalent relation. Functions out of quotients. How do you define such things? Okay, what's the ingredient? What are the ingredients that I need? I need an equivalence relation of the set because that's a quotient. An equivalence relation on a set X. And remember, I want to define functions going out the quotient X over the equivalence relation. And I'm going to start with a function going out of X. Let's call that F. So why here is any sense? And it turns out defining functions, so maybe I should write it. This is what we want is some way of defining function going out of X over quotient to Y. And the answer is they come from functions from X to Y. And how? Here's how. Part 1 of this theorem. we can define a function if f has the following property. So the property will be for every 2 points, x and y in x, if they happen to be related, then f will collapse them to the same points. So if that's the case, whenever 2 points are related that f of x is f of y, then we can define a function which will be unique with the following property. Unique function, and since it's going to be entirely defined using f, I would call it f bar going out of the quotient to y as we wanted, given by the following rule. F bar at a class. So remember, this is how things look like in the quotient. So this is a generic element in the quotient. F bar at the class of x is just going to be f of x. So this is sometimes confusing. But what's actually going on here is I'm using this formula, and you might say, well, that formula always makes sense. You don't need this extra weird assumption. But the thing is, if you don't have this assumption, it's like I'm using x to define this thing, but what I actually have is the class of x, not really the point x. But in other words, if instead of giving me the class of x, you take y, which is related to x, well, you will have the same class, and here you will not know whether you want to put f of x or f of y. But what we're saying is these two things are the same. And that's exactly what's going on here. Since that's the case, the function f is continuous on each equivalence class. And now you can just define a new function by taking its value at any member of the equivalence class, because that will always be the same. So you have this function, this property, and let me say how you usually use this. What this means is the function f bar satisfies. Sometimes you don't want to use the definition, but you want to use it satisfies the following. F bar composed with pi, my projection or my quotient map is just f. And why is that? Because this is exactly pi of x, right? So this is what this is telling. F bar composed with pi is f. Okay, that's the first part of the theorem. How do you define functions out of the quotients? Parts 2 and 3 are about properties of f bar. So the first property I want to say about f bar is assuming that f bar that you can define f bar. So assuming that this is the case, namely f of x is f of y whenever x is raised to y, then the image of f bar, so that's the image of f bar, is going to be exactly the image of f. That's great. So in particular, if f is surjective, then the image is entire y, and also will be f bar. And why is that the case? Well, because of this. With f bar, you can capture exactly the same things that you can capture with f. That's all that's going on here. And part 3 of this theorem is, well, I just said something about surjectivity. Now I want to say something about injectivity of f bar. So this will look very similar to 1. So assume that for every x and y in x, previously I said x related to y implies f of x equals f of y. That's what I need here to define my f bar. So maybe I can color this. Now, if that's if and only if, of course, you can define your f bar and it's going to be injected. So in other words, we know how to define functions going out of quotients, how to compute their images, and we have a criterion to decide whether or not they're going to be injected. So this is kind of the fundamental theorem about quotients. And let me just uh, put some name into this kind of thing, because we're going to use that a lot of times. So definition. I will have the same setup as before. So if f from x to y is such that f of x is f of y whenever x is raised to y, we're going to say that f descends to the quotients. Okay, why do we say such thing? Well, usually it's because this is what's going on. You can go from x to y using f, and you can descend to the quotient of x by the equivalence relation using pi. That's independent of f. But what we're saying here is your f descends, comes from something below it. So that's kind of what's going on. And we also say, instead of descends to, we say that f factors through the quotient. And why do we say that? Well, we say that because what's actually going on, let me go up to my formula here, is this. F factors as something times our quotient map. And I will mostly use descends to, but I just wanted to know factors through the quotient is also it's also very competent wording for this situation. Okay. Example. Let's go back to our example from before. So we have, I don't want to write this again. So we have the example close interval 0, 1, where we're identifying 0 with 1. Here, to define a function, so remember it looked like the quotient was going to be in bijection to S1, but to define a function from 0, 1 over the quotient to S1, we just need to define a function. Let's call it f from 0, 1 to S1. But I don't need just any function. I need one that's going to identify points that are related. But here, the only things that are related are the extremes, 0 and 1. So the only property that I need is I need f of 0 to be f of 1. Because those are the only 2 points, the 2 different points that are related. So we know how to do this. We've been here before. So our favorite example of such function should be from our experience, and also because it just makes sense, this sort of idea of running through the circle counterclockwise, say. We can define f even by f of, let's say, t is going to be, first coordinate is cosine of 2 pi t, and then sine of 2 pi t. Of course, this function At 0, you will be at 1, 0. And at 1, you'll be at the same point. So f of 0 is going to be what 0, which is also f of 1. And thus, it descends to the quotient. Sometimes we also say it induces a function. Induces a function f bar out of the quotient to S1. And this is given by the same kind of formula. Given by f bar at the class of some point t is going to be, well, I just use the same formula. So I know I have the function because I used the first part of my theorem. But now, and note things, first thing I want to note is f is surjective. Because everything in the circle looks like cosine of 2 pi something, sine of 2 pi something. So f is surjective, and by our theorem, so is f bar. And the second thing is, if I want to study whether or not f bar is injective, I need to prove the following for any x, y in 0, 1. F of x, or maybe let's say x is related to y, if and only if f of x is f of y. So what I'm saying here is the only way for the function to collapse 2 points is if these points are related. And that's true because in the interior, the function is injective, and the 2 points, they collapse to another point. So this is true, and that means that our f bar is injective. In other words, we just hook up f bar from the quotient to S1 is a bijective function. And this justifies our previous idea. So let me go up. Justifies our previous idea. What we're doing is we're pasting these two elements on the same one, and then everything else remains the same. Okay. Very good. Now, what we're going to do next time, well, what we did is just set theory. We discussed equivalence relations and then how to define functions going out of quotient sets. And next time, we're going to assume our X has a topology. So it's a topological space. And what we're going to do is define, hopefully in a natural way, using our quotient map, a topology on the quotient set. So that'll be next time. And yeah, that's it for today.